Okay. Good afternoon, everyone. I'm Jiaqi Guan, a computer science PhD student at UC, advised by Professor Jian Peng. And today I will talk about my research about energy-inspired molecular conformation optimization. Molecular 3D structure is important because it is informative to molecular property predictions like quantum properties. And if we can efficiently and accurately generate molecular conformation, we can also unlock lots of new opportunities, such as screening for protein targets. However, we don't always have this molecular 3D structure information. What we usually have is the molecular 2D graph. So given a molecular 2D graph, how to predict its 3D structure becomes a very important problem. Formally, a molecular 3D structure is also called the conformation. It's a 3D Cartesian atom coordinates of the molecule. And our model will be given a molecular 2D graph, and it needs to predict multiple conformations because for each given molecular 2D graph, there usually exist multiple stable conformations which have a low energy. And previously, there are many approaches are proposed to solve this problem. One important approach is molecular dynamic simulation, where atom coordinates are sequentially updated based on forces. And these forces can come from the density function theory or the handcrafted force field. There usually exists a trade-off between the accuracy and efficiency. For example, DFT-based molecular dynamic simulation is usually very accurate, but also very computationally expensive. Instead, force field-based molecular dynamic simulation are very efficient, but they are not accurate enough. So more recently, there are many deep neural network-based approaches are proposed to solve this problem. Some of them are two-stage approach. For these approaches, they will first generate the distance matrix, then reconstruct the 3D coordinates from this pairwise distance matrix. For example, the GraphDG and the CGCF. They are utilize different kinds of generative models like variety autoencoder and the continuous normal flow. However, for these two-stage approaches, there will exist an information loss between the reconstruction from the pairwise distance to the 3D coordinates. So more recently, some one-stage approach is proposed. For example, the ConfGF, which utilizes the denoising score matching techniques. And it can estimate the one-step coordinate gradient. And after the model is trained, it can utilize some sampling methods like Langevin sampling to generate a stable conformation from the initial one. And in our work, we formulate this problem from a different perspective, specifically from an optimization perspective. Our motivation is very straightforward. Nature has an energy function for the conformer, and the energy function actually governs an energy surface. For each stable equilibrium conformer, it corresponds to a local minimum on the potential energy surface. So to get a conformer with lowest energy, actually we can feed the model with an initial conformers, and we can navigate the energy surface or perform the gradient descent by updating the 3D coordinates to gradually optimize the initial conformer to the low energy state. However, the problem is that we don't know the exact formulation of the energy surface. So here comes one solution. We can use the graph neural network to learn the gradient field of the conformational energy from the data. We can use a graph neural network to estimate the atom coordinates gradient. And in this way, we can perform such one-step optimization to transform the conformer to a lower energy state. And if we stack such layers together, the neural network actually mimics the all optimization process. However, it needs to be mentioned that the neural network needs to be 3D rotational and translational equivariant. That means no matter how we translate or rotate the initial conformer, our neural network's output should rotate or translate in the same way. And next, we will see our models derived from the energy minimization perspective will be naturally SE3 equivariant. The recipe for deriving the energy-inspired models is also simple. First, we need to assume an underlying energy function. For example, we can assume a molecule's energy related to all pairwise distance of the atoms. And then we can take gradients of this energy function with regard to the conformation X. And we can reach to the update formulation in the red box. And such an update formulation will be naturally SE3 equivariant. And the proof is also very simple, and the rationale behind it is that the energy function is SE3 invariant. So the gradient field of this energy function will be naturally SE3 equivariant. And based on different assumptions on the underlying energy function, we can also derive different kinds of neural networks. For example, if we also assume that the molecular energy corresponds to the bond angles, we can write down the 3-atom model as this. And following the same way, taking the gradient of this energy function, we can achieve an update formulation of the neural network in this way. And such a perspective can bring some benefits. First, it is more principled than previous heuristically proposed equivariant networks like EGNN. And also we avoid using some complicated spherical harmonics-based techniques like used in the SE3 transformer. And also compared to the recent state-of-the-art approach conf-GF, our model enjoys the faster sampling time. And for the experiments, we test our model in 2 different settings. The first one is a molecular conformation optimization setting, where the target is to predict the lowest energy conformer. And we compute the mean and median RMSD to evaluate our model. And the second setting is a molecular conformation generation, where the goal is to generate a set of low energy conformers. And because our model is a kind of optimization model, to apply our model in this setting, we apply the optimal transport loss. It means we will feed our model with different initial conformers, and our model will optimize these conformers to some low energy state, and we will compute the matching between the conformers in the generation site and the conformers in the reference site, and compute the corresponding L2 loss and minimize them. And for this setting, we compare our model with some previous proposed deep generative models. And for the first setting, we can see that our different variants of our models can achieve a better RMSD compared to SE3 transformer and the EN equivariant graph neural network. And from the visualization results, we can also see that our model can generate more realistic conformations compared to other baselines. And we also prove that our predict conformers can be helpful for downstream applications. The first example is that we use a precise fall to predict the humolumo gap with reference conformers or the model predict conformers. And we found that our predict conformers can have the highest Pearson or correlation factor with the one predicted with a reference conformers. And the second example is that we use predicted conformers to train a neural network, Schneid, to predict multiple quantum properties of the molecule. And we can see that with our predicted conformers, it can achieve better results compared to those models with different predicted conformers. And for the second setting, we evaluate our model in terms of the coverage score, which represent how many molecules in the reference site can be covered by our model, and also the mismatching score, which means how many molecules in the generation site cannot be matched in any conformer in the reference site. And also we compute the matching score, which means the lowest RMSD of each generated conformers to the conformers in the reference site. And we can see compared to previous generative models, our models can achieve higher coverage score, lower mismatching score, and better matching RMSD. So that's basically my work, and thanks for your attention. Is there any question?
This is Saurabh Sinha. Great talk. You presented great examples of where the method was able to improve the conformer prediction. In your experience, what were the characteristics of the cases where it wasn't able to or did badly? So could you characterize what the fail cases are?
Yeah, I didn't show some failure case in the slides, but actually the thing is that the difficulty of this problem increase with the more numbers of the rotatable bonds. So more rotatable bonds means more flexible of the underlying conformers. So for the molecules in the genome drug data set, it is much more difficult than the molecules in the QM9 data set, where the molecules only consist of up to 9 heavy atoms. So for some failure case, I think I didn't do such visualization, but if the molecules have many rotatable bonds, it will be difficult for the model to reach the lowest energy state. So, but it can also generate some low energy state conformer. Yeah.
Okay, so but that's I mean that sounds like a general problem that any search method will face. If there's it's not specific to your way of learning the gradient, right? Or is it? I mean, is there some?
Yeah, that's a good point. Yeah, I think it's a good direction to carefully evaluate the failure cases and to figure out some drawbacks of this approach.
Yeah, yeah, great. It's working well. That's great, but you know, it's also important to find out where it's not. So
yeah, sure.
Great talk.
Yeah,
Thank
thanks
you
for your question. Yeah, another question.
Hi there, great talk. I have a question in terms of the charge structures. Do you have any issues when it comes to conformer generation, or see any issues when there are charge structures or significant resonance structures available for your conformer generation, or do you see repeats of a lot of them or low deviation?
The charge structure means that some charge in the atoms?
Yeah, like for example, with number 5, there's a nitro species on that furan. Do you see any issues when it comes to charge structures or resonance structures when it comes to your conformer generation methods?
Yeah, I didn't see many problems of the charge molecules. Because for our new network, we also consider the atom charge as the feature of the atom. But yeah, you mentioned me there. There exists some few cases that the chemical molecules our model cannot handle them. But for because we minimize the L2 loss of the distance matrix, so it cannot differentiate the chemical molecules. So that's a point that our model need to figure out. But for the charge atoms, I didn't see many problems in those molecules.
Okay, thank you.
Thanks.
Any other questions? Oh, we can see if there are questions in the chat. Okay, if there are no other questions, thanks to Jiaqi for the very interesting talk. And yeah, I think we're going to take a 11-minute break now, and we can come back at 2:30 p.m. Central Time again for our following talks. Yeah, thank you.
Yeah.